this point in math, should be pretty comfortable with quadratics. We see it through a lot of our levels of algebra before getting to trigonometry. Rational expressions, though, maybe still feel kind of new, and there's a lot of rules that go with rational expressions. So while you should have seen these quite a bit before this class, I am going to go pretty slow through this video to just really emphasize what we can and also, more importantly, what we can't do with these expressions, because there are a lot of illegal moves here that are pretty common mistakes. But if we make those mistakes, it will kind of mess up our identities and how we're proving them. All right, so for this case, this first case here, we are adding two terms together. So we have these two separate terms, and in order to add fractions together, we have to have the same denominator, which we do not have here. And if it helps, something that I visualize every time I have a kind of an expression within a denominator and the numerator, but kind of most importantly, the denominator, you want to visualize parentheses around here. That subtraction and that addition there, it locks them together. So those have to be stuck together. So to create a common denominator, something I need to think about is making a least common denominator. And with expressions, it'll often come through as a multiplication of the two values. So what I can do is, to make a least common denominator, I want to see 1 plus x times 1 minus x. That'll be what I need in order to make a common denominator. So what we would do is focus on one term at a time. So if I look at this first term, what I'm going to notice is that I'm missing that 1 plus x from the denominator. So I need to multiply that 1 plus x on there. But I can't just multiply the denominator. That would change the expression. What I need to do is actually be multiplying by a version of 1. So that means whatever I multiply the denominator by, I need to also multiply the numerator by that same value. So when I do this, in the numerator, I'll have 1 times 1 plus x. So that means I'll end up with a 1 plus x in the numerator. And then the denominator, I'm going to have a 1 plus x times 1 minus x. And it's like, in this form, you might be inclined to cancel that out, but we don't want to, because the whole point was to get that multiplied on there so that we have this big denominator. Now I'm going to do the same exact thing to the second term. I have this 1 plus x there, but I'm missing the 1 minus x. So I need to multiply on that 1 minus x to the denominator, which means I also need to multiply it on to the numerator. So that'll do, so I'll have this big plus symbol in the numerator, 1 times 1 minus x over 1 plus x times 1 minus x. And now I have my common denominator. I have the same thing in the denominator, which means I can add together the numerator. So a little fraction review here. We add the numerators. So in long form, it would look like 1 plus x plus 1 minus x. And really, there's technically parentheses here, but when you add between them, that's not too important. If you have subtraction, that's very important, because that subtraction would need to distribute through to that second expression. All right, over 1 plus x, 1 minus x. And what I do is I leave the denominator factored until the very end, because if we have something we can cancel out with the numerator, we want to do that. But first thing we have to do is completely simplify that numerator. Now those x's will turn into a 0, so really I just have a 1 plus 1, which is 2. And seeing that 2 there, I'm going to see I'm not going to have anything to cancel out with that denominator. So what I'm going to do is FOIL that out. So 1 times 1, that's our difference of squares. So that'll be a 1 minus x squared. And that would be all done there. So creating common denominator by multiplying, it has to be a version of 1 because we're dealing with expressions here. We can't just go changing things because we don't have another side of the equation to balance it out. So we're always multiplying by some form of 1 so that we're not really changing it, but we're kind of changing the appearance of it. All right, so let's look at this process, but for this expression. So Same idea, and it's just that we could visualize that those are x's there. I'm just going to go through this a little more quickly since we went through the process. We're just changing x to cosine. So I'm missing that 1 plus cosine of t, and I would need to multiply the numerator by that same thing, times, and then over here I'm missing the 1 minus cosine of t, and I would need to multiply the numerator by that as well. So my first term will have 1 times 1 plus cosine of t over this 1 plus cosine of t times 1 minus cosine of t, and then we're adding that with 1 times 1 minus cosine of t over 1 plus cosine of t, 1 minus cosine of t. Now adding these together, 1 plus cosine of t plus 1 minus cosine of t, those cosines are going to turn into a 0. So really I'm just going to have a 1 plus 1, which is 2, over, and then I'm going to do like what I did over on the left there, is we would FOIL this out and it would give a difference of squares, which would give us 1 minus cosine squared of t. And when we were working with x, that was the end. But something I want to bring through here is the idea of our identities. So that Pythagorean identity, pretty much whenever I see sine squared or cosine squared coming up, and especially when there's a 1 next to it, because that really came through in a lot of those other forms of identities, something I do is I just think, can I use the Pythagorean identity here? So what I do is I go and do some side work. So I'm going to bring up my Pythagorean identity, which was sine squared t plus cosine squared t is equal to 1. And what I'm going to see is, can I make 1 minus cosine squared of t? Well, my 1's over on that right hand side, so what I'm going to do is subtract that cosine squared of t from both sides. So that would leave sine squared t on the left, and then I would have 1 minus cosine squared of t. And what that would do is that would mean I could substitute this expression where I have addition or subtraction there and just replace it with a single term. And that'll be a part of simplifying. So what I'm going to do is go one step further and go 2 over and replace that 1 minus cosine squared with sine squared. And that's fantastic. Just like that, I have this expression that's only dealing with a single trig function. However, we could go one step further to make it even simpler, would remove the denominator. So what I could do is think of this as 2 times 1 over sine squared of t. And 1 over sine, remember 1 over sine is equivalent to cosecant. And it's the same thing for when you have a variable there. So really this is the same thing as 2 times cosecant squared of that variable t. So that is also a simplified form. It's kind of hard to know when to stop with these. Often if you can get it in terms of sine and cosine, that's fantastic. I personally see this as a little simpler because then we don't have to be dividing by anything. It's just multiplication of 2 values. But really, these are pretty equivalent in terms of simplification, mostly because both of them just deal with a single trig function. So that's something to think about, is when we get through these and we're simplifying, we also need to keep in mind that Pythagorean identity, as well as those reciprocal and quotient identities that are in there. All right, this one, x plus 1 over x. So what I would want to do is where I see x there, I want to think of this as x over 1. And in order to add those together, I need to think about a least common denominator. In this case, we only really have one denominator. So the least common denominator is just going to be that value of x. So I only need to adjust one of these terms. I need to adjust this to have a denominator of x. So I would come through as multiplying the denominator by x, but it has to be a version of 1. So I would do x over x. So x times x is x squared, over x times 1, which is x, plus 1 over x. Now I can add the numerators together, so x squared plus 1 over, and then that common denominator of x. So that's how we would add those together. And there's nothing else to simplify here. Again, I said I was going to emphasize things that you can't do here. A common mistake would be to cancel out x values, but we can only cancel across multiplication and division. If this was multiplying with 1, then yes, absolutely you can do that. But basically what I keep in mind with these rational expressions is that addition and subtraction always makes it more difficult. So the only way we could cancel out anything up in that numerator is if we saw that entire x squared plus 1 also in the denominator. That addition and subtraction symbol are going to group them together. And if it helps, you can always draw parentheses to kind of help out to see those are stuck together. So we can't start canceling things out inside because it has to cancel as a whole rather than separated pieces, all because of that addition symbol right there. All right, so here, we're going to do pretty much the same thing. So this is tangent of t over 1. And I'm going to go ahead and multiply by tangent of t over tangent of t so that I get that common denominator of tangent. So in the numerator, this is going to make tangent squared over tangent t plus 1 over tangent. Now I can add the numerator together. So tangent squared of t plus 1 over tangent of t. Now, something I would start doing here is after we got those added together into a single term, I would start substituting in sine and cosine and start simplifying down. However, I'll tell you now, I did that already as some side work, and it gets messy. You get to a simplified expression, and I'm going to do that in another way, but it's like if you kept this as tangent and went and then made the substitutions of sine and cosine, it gets pretty rough. So what I'm going to show you to the side here is where there's this benefit to just substituting in sine and cosine at the beginning. This is going to bring through some different rules that we're going to be working with, but it's a much shorter process. And I mean, go for it. If I'm just not going to record a video that goes long into this kind of rabbit hole of getting to that simplified form with this, but try it out. Plug in sine and cosine, start adding together fractions and getting them moving pieces around. And you can get to the same spot that I'm going to do over here, showing that if we just substitute sine and cosine at the beginning, it's a bit simpler. So what I would do is where I saw tangent of t, that would be sine over cosine. And then plus 1 over sine over cosine. All right, complex numbers. This is something we need to review as well of what happens when you have a fraction within a fraction. And basically you look at the denominators. So what I can see is I have this denominator of cosine of t, and I want to clear that out. So what I'm going to do is multiply that denominator by cosine of t. However, whatever I multiply this denominator by, I need to multiply the numerator by the same thing so that really it's just this version of 1. So what that's going to do is I'll have sine of t cosine of t plus cosine of t over sine of t. Which makes sense, we're seeing cotangent over there because it was 1 over tangent. So we could have even done that, like saw that was cotangent and knowing that that would make cosine over sine. So many of these pieces relate together. All right, so I want to add together these two fractions, but I need a common denominator. So here I have cosine, but I need to multiply on sine. So I'm going to multiply by a version of 1 with sine, and over here I'm missing cosine. So I need to multiply on a version of 1 with cosine. So the numerator of this first term, sine times sine, sine squared over sine times cosine, plus cosine times cosine, so cosine squared of t over sine t times cosine of t. Now I can add the numerator together. So that was sine squared plus cosine squared over sine times cosine. And right up here is our direct Pythagorean identity. So what I can do is we had the relationship that sine squared plus cosine squared is just equal to 1. So this is a nice one where we can make this whole substitution of where I see sine squared plus cosine squared, and that's the same thing as 1. That makes it so much simpler. And then our last piece is, I could think of this as equivalent to, I can write it down here, 1 over sine of t times 1 over cosine of t. Well, 1 over sine of t is just cosecant. 1 over cosine is secant. So, much simpler form there. We're working with two trig functions, but it's just multiplication of two trig functions. Typically, we think of multiplication as our simplest form. We kind of want to get rid of this addition mixed in there with multiplication and division. So, if you substitute in sine and cosine here, you can go through this whole route of simplifying down using similar things we did here and get to that same spot. And if you just want to trust me on this, making that substitution for sine and cosine at the beginning makes it a lot easier rather than working with here you'd have a fraction plus 1 over a fraction in the denominator. Here we only needed to work with one mixed number with a fraction in the denominator, and that was easier to clear out. So this is kind of the work we're doing with identities and simplifying down and making the fact that this expression here, this cosecant t times secant of t, is exactly equal to what we started with right there. So this proves an identity that if we saw this expression, it's the same thing as this. All right, 2 more here. So 1 over y minus x squared over y. Now these have a common denominator, so what I would do is just combine the numerator, 1 minus x squared over y. And that is done. That's all we would do there. So let's see what happens when we work with this one. So in the numerator, we'd have 1 minus cosine squared over our common denominator of sine of t. In the numerator there, I'm seeing 1 and cosine squared, which is making me think of the Pythagorean identity. So that tells us sine squared plus cosine squared is equal to 1. And what I can do is recreate that 1 minus cosine squared by subtracting cosine squared from both sides. So that shows me I can make this substitution with sine squared. So that numerator is the same thing as sine squared of t. We still have sine in the denominator. And then these cancel out just like we do in algebra. Like if this was x squared over x, this would simplify to just x. Same thing here. It's like one of those, it's like in the numerator we have sine of t times sine of t divided by sine of t. Well, one of those signs is going to cancel out and we're just going to have 1 left over in the numerator. So sine of t is exactly equal to all of that business up there. So if we ever saw this expression again, we just proved that we verified that identity. So if we saw this somewhere, we know that's equal to sine of t. All right, our last one here is working with mixed numbers, which we saw a little bit in that second example. I'm going to rewrite this just because visually it helps my eyes to see it in this form. So I can kind of clearly see those numerators and denominators within numerators and denominators. All right, so I'm just going to focus on this first term. And what I want to do is I want to get rid of that denominator within the denominator. So what I would do is multiply by y squared so that those will cancel out. But whatever I multiply the denominator by, I also need to multiply the numerator. So with that, what I'll get is in the numerator, I'll have y squared. In the denominator, we get this cancellation of those y squared values, so we would just have 1 left over. Now plus, oh, I don't need that in blue, plus, and then over here, we're going to do the same thing. So I want to get rid of that denominator of x squared, which means I need to multiply the numerator by x squared as well. So we're going to have x squared in the numerator, and then the denominator, those cancel out, so we would just have 1. So y squared plus x squared is where we would end there. So this one looks like it doesn't have mixed numbers, but what we're going to do is that step of substituting in sine and cosine. So really, this is the same thing as 1 over sine squared plus 1 over cosine squared. And I'm going to do the step that I did to the left there of clearing out those denominators within each term. Clear out the denominator. Squared, that's what I was missing. So down there, all of those values will cancel out. So up in the numerator, I have sine squared plus cosine squared. And with our Pythagorean identity, that is exactly equal to 1. So I verified this identity that if I have this expression up here, I could really just substitute in 1 because we proved the process there. So that was a good mixture of these rational expression rules that we have and how to work with these numerators and denominators. Just keep in mind that if you multiply, you have to keep this balance because it really should be multiplying by 1. It's just we kind of create these versions of 1 that we can work with. And then just keeping in mind that Pythagorean identity along with the reciprocal and quotient ones so that we can simplify our expressions in the process as well.